So let's the science speak now. We will start with Professor Paul Alivisatos, very rich in accomplishments and other prizes, but Dan David Prize, including the Wolf Prize in Chemistry, the Linus Pauling Medal, the Von Hippel Award, and the American Chemical Award in Chemistry of Materials.
Well, 1 second. The first prize, I think, was the Sackler prize.
That was for Professor Mirki.
Sorry.
Yeah, that was for Professor Mirki. Maybe you should have this prize as well. Okay, Paul, please. Yeah.
Okay. So maybe I just need to switch this. Is that, if I saw what happened earlier, I think that's, so let me just begin by thanking you and saying just how honored I am to have been recognized with this award, with the Dan David Prize, and how happy I am to be back with my friends in Israel. I'll just say a word at the beginning that to me, I feel like in Israeli society there's a deep reverence for all forms of human creativity, and that's a wonderful thing for any society to have. And so this award, I think, expresses that real cultural strength of seeking to develop creativity in all of its dimensions. And I think that's just wonderful. And also to say that over many years I've had many interactions here with the people at Tel Aviv University, and it's very thrilling to see the development of nanoscience here, which is really becoming very strong. And so it's wonderful to be back with you and to have this opportunity to share some of our work. And in the spirit of the prize, where we have past, present, and future, I will also take a few minutes to talk about things that we have accomplished over time, some from the past, and some from the present, and some from the future. Partly also in order to give you, those of you who are not from the world of science, the tools that you need so that by the time you leave the room you are a complete nanoscientist and have all of the information that you need to go forward. When I was a teenager, there was this show in the United States, television show, Saturday Night Live, which still exists, and there was a little skit with a comic named, a fellow who, the character was Father Guido Sarducci, and he had what he called once a skit, which was the 5-minute university. And in the 5-minute university, you learned in 5 minutes everything that you would remember 5 years after you had received a university degree in a given subject. So this will be the 5-minute university version of nanoscience. And so we'll say a little bit about quantum dots, and then past, and then a little bit about present and future. So for me, I will start with my discussion around the scaling laws. And the earliest, the phrase atom in Greek means that which cannot be divided. And of course, what brought about the first thinking that the world might actually have atoms was a thought experiment in which you took a piece of gold and imagined breaking it into two and thinking, well, these two things are essentially the same. They have the same density, the same melting temperature, they are the same color, they basically are the same thing, just divided. And if you continue in that thought experiment to divide it over and over again, at some point it becomes so tiny that Democritus reasoned originally, eventually it would become grainy, matter would become grainy, not continuous, and there would reach a point where when you divide it, it was no longer the same. It will no longer be the same. And in fact, there will be a point at which you divide it, and you cannot divide it again. That's, of course, the atom, or the indivisible, the unit, the grainy unit that makes up matter. And nanoscience sits right at that edge where material has first reached the point where when you divide it in two, the two pieces are no longer the same. And the properties now depend upon the size. And so when we make a material half the size, each time we do that, the properties all will change. And so, for example, the simplest one to imagine is melting temperature. And here is a very early study of ours which measured the change in melting temperature of a crystal, a semiconductor crystal, as a function of its size. And so why does this happen? You can see there's an enormous reduction in the melting temperature as a function of the size of the crystal when it becomes very tiny. And you can easily imagine this because every atom in the crystal is linked to every other. And the more they get linked together, the stronger the crystal becomes. But if half the atoms are on the surface, they have no partner on the other side to link to. So they're a little bit easier to move around. And in fact, that surface to volume scaling is what leads to a variation of the melting temperature with something like 1 over the radius of the particle. So that's a famous scaling law. And in fact, it's quite important for what I'm about to teach you about. Now, here's the second scaling law that you need to know. And this is one everybody encounters at some point probably in their life. When you go to the jewelry store to buy a diamond for your significant other, you are always faced with a dilemma, which is, most people at least, unless you are in the 0.001%, at some point you have to decide that there's a certain amount you're willing to spend, and that will tell you the size of the diamond you're going to get. And you could say, well, that's true, but what if I just doubled the size? What would happen to the price? Well, it turns out it will go to 4 times. So that's a simple scaling law that we can all relate to very quickly because that pretty soon places a bracket on what size you're going to get. But why is that? That's because you want to buy a crystal of high quality. That determines its optical purity. And imagine now that you have a crystal which in the course of its growth, somehow a mistake has occurred. Typically they happen. And so at some point there is an error inside this crystal that ruins its optical properties. And now you would like for it to go away. Well, it will eventually go away. It turns out the time scale is exponential with volume. So as a crystal becomes larger and larger, the probability that a defect will eventually work its way out depends so strongly upon the size. And the consequence of that is that the diamond becomes very rare when it's large and high quality at the same time. It's unusual to find, and it's difficult to make. Now, that's a that is a kinetic defect, a defect that happened because of the growth rate. There are also equilibrium defects, which are ones that are present if just the number of atoms is very large. There will be a defect in there at equilibrium. But it turns out that for a typical inorganic crystal, a few electron volts, 4 or 5 electron volts per atom binding energy, the probability that there will be a defect in a crystal of 1,000 atoms is actually quite small for equilibrium. Okay. So if there's a defect present because the crystal was grown too quickly, then it will take a long time to anneal out if the crystal is very large. Well, in nanoscience, we turn that on its head, upside down. And it says, we say, okay, then if that's true for a really big crystal, what if my focus is on a really tiny crystal? If it's only 10 atoms across, the time to anneal a defect out is actually much less than a second. And in fact, because the melting temperature is low, what I just showed you a minute ago, I can take a material which ordinarily has to be made at a very high temperature under very complex chemical environment of extreme purity, and instead I can take that material and grow it under very, very simple conditions at a low temperature. And the defects will simply go out to the edge. And because the crystals are so small, the equilibrium defects will only be one defect in very, very large number of tiny crystals. I can have a huge number of tiny crystals, and at equilibrium there will only be maybe one of those crystals has a defect inside of it. So as a consequence, one of the really beautiful things about nanoscience is that it's possible to make very perfect crystals, and that these crystals are very robust. Now, that doesn't mean you will always make perfect crystals. It's possible even to make a nanocrystal very badly. But if you pay attention to the conditions, they favor the formation of a good crystal. And one way that we saw this many, many years ago was by studying structural transformations in which we took nanocrystals and placed them at high pressure and temperature. And what we could show was that a crystal can change its volume by undergoing a structural transformation from a not dense phase to a dense one under pressure. And that when that happens, a crystal can change its volume by as much as 20, 30 even %. And the crystal will stay intact. It simply changes its shape. And it can go back and forth and cycle between these two different crystal structures. That's a scaling law, by the way, which today finds its application, in a sense, in batteries. When we charge a lithium ion into a battery material, there's a big volume change. Well, if it's made out of tiny particles, then the volume can change reversibly. And so that's an example of one of the scaling laws finding its use in practical energy technology. So one of the consequences of these areas is that it's possible to make high quality materials rather cheaply, and to make them at large volume. So the quantum dots that you might have seen last night in the movie that are made inside original work in a tiny flask about that big, today in a factory nearby Berkeley are being made at the scale of 25 tons a year and then put into various displays, so that it can scale very readily. And the cost can remain quite low. Now, so you've seen, you now are armed with two scaling laws, melting temperature and the idea of a nanocrystal as a structural domain. The somewhat more complex scaling law that turns out to be quite important is one that's intrinsically quantum mechanical. So our intuition starts to fail us a little bit, but when we have a crystal, inside of it, if it's a semiconductor material, we can promote an electron, a bonding electron, into a non-bonding state. That electron can move around the crystal now. That's how we get all of our electrical logic taking place inside a phone or something, is we've got a material where we can switch whether the electron is conducting or not by promotion of an electron. And it turns out that that electron is a wave, or it's extended. It's not isolated into one bond, but it extends over a certain volume. And that extension is, in fact, a vital part of the behavior of small semiconductor particles, as was shown originally by Louis Bruce. So if we look carefully inside a small semiconductor crystal, the smaller it gets, the more the electron that is a wave is forced to occupy a smaller volume. And in that smaller volume, the electron is forced to move more and more quickly. As you compress it down, its motion becomes faster. Why, that means that in order to create the electron, you have to give it that extra energy to move around. Hence, the band gap depends so strongly upon the size. Now, there's something quite important about that. well, first of all, let me say that, there's some technical details here that I won't go through because they're technical and only, of interest to people who actually study these things. But in any kind of material that you study, sooner or later there's a place where the wild things are. And these are things that you can't quite easily explain as much detail in a simple model as you would like. And in the nanocrystal case of the semiconductors, all the wild things are on the surface of the crystal. And the surfaces of crystals have been very, very hard to analyze. So in the future section, I will tell you our dream about how we might one day be able to measure the position of every atom on the surface of a nanocrystal. But to date, that's never been done. So here we have a funny new material. It's a basic building block of modern materials, a nanocrystal. And that building block, we now can make very high quality, but about a third or a half of the atoms, we can't tell you their exact position yet. So that's why it's called the wild things. The good news is we can just eliminate that surface by burying it inside another. We can grow one crystal around another, and when we do that, this interface can become very electronically well defined. And that's essential to all of the actual materials that are used. Now, one thing that's very important about these tiny crystals is that the electron, when it's excited, is very delocalized. It's delocalized over that crystal. And so I'd like us to stop for a moment and think about that and its applications for biology in the following way. Imagine that I have a molecule, like an organic dye, that has 20 atoms in it. So these are the colors that we use for food coloring or for clothing coloring and so on. Many of them are made out of organic molecules. And when we excite that molecule, an electron is, a bond is effectively broken. One bonding electron is promoted to a higher excited state. And that excitation then relaxes by the emission of light. That's what a dye will do. And the thing to think about is the issue of volume. It's a very simple idea, namely that if I have an organic molecule where there's an excitation of this type, and that excitation is delocalized over 20 atoms, the molecule is in danger of breaking. There are 20 bonds that hold the molecule together, and one is broken. And in the course of that extra energy, there's extra energy inside that system, there's a chance that it will come back by the relaxation that emits light. But there's also a chance that that energy will end up, in fact, rearranging the atoms inside that molecule. And that, of course, is what destroys the molecule. It's why if you take a colored fabric and stick it outside in the sun, and you go back a month later, it's faded. So a nanocrystal is quite different because that electronic excitation is now delocalized over 1,000 or 10,000 atoms. And as a consequence, the probability that the atoms will rearrange to break the crystal becomes very low. And this is fundamentally, at a very simple level, why it is that a quantum dot is photostable compared to an organic dye. It's also why it has a more narrow emission spectrum. The light that comes out is spectrally more narrow in energy because in the organic dye, when the excitation takes place, all the bonds change a little bit. The molecule essentially changes its configuration. And then when it comes back, again, there has to be another change. So that alternation of structure broadens the spectrum out. And the quantum dot, in contrast, has a much narrower spectrum. So the first application of these quantum dots that we developed some years ago was, in fact, to take them and introduce them inside cells where they could be used for labeling. Here's an example of actin fibers in a fibroblast cell that have been decorated with quantum dots. And over here is the same kind of fiber treatment, but with a common organic dye. And during the time that I was speaking, you could see that the dye bleached and the quantum dot did not. And that's because of just what I told you about, that they're more stable. So today, quantum dots are available for use, and about 10,000 research groups around the world actually purchase and use quantum dots for labeling in various medical research experiments. And in the event that you have a biopsy and somebody wants to examine the tissue, most probably the tissue will be treated with the quantum dots in order to image the tumor and make some determination on it. Most labs that use those things are using quantum dots. Now, the other place that these things have found a commercial use, these semiconductor materials that can emit light, that are made in the ways that utilize the low temperature and so on, is in displays. And the way that is done is to have a blue light-emitting diode underneath that takes electricity and converts it to blue light, and then on top a film that contains the quantum dots inside, two sizes, a green and a red, and then that gives you the three blue, green, and red colors that are required, that combination of three, to make any color that you might observe with your eye. And these quantum dot displays are quite interesting. You'll remember I told you that the emission spectrum is narrow, and also by changing the size just a tiny bit, we can tune the color. So, and we've learned how to control the sizes very precisely. And that's very important. If you're used to at all looking at what's called a CIE diagram, it turns out that your eye perceives three different colors that are the peak points of the receptors in your eye, and every other color is made up by ratios of those that are impinged upon. And so the quality, the color quality of a display depends on the degree to which the three primary colors, red, green, and blue, that are used to build up all the others, the extent to which they actually match the corners of that diagram. The better that they do that, and the more pure the color is, because if it's a very broad spectrum, then one channel leaks into the other. You're trying to denote green, but in fact some is appearing as red. Then that reduces your capability to make all of the colors be represented that your eye can see. And this white diagram, or all these white dots that you see here, are ones which were obtained by a person who simply went around in the natural world with a colorimeter and measured the colors of objects that we encounter in life, okay? And then this black one is the range of colors that's most probably reproduced by my computer display, which already is quite a bit better than what this projector can show. So there are many objects in the world that we encounter whose colors cannot be reproduced by the colors that are in a typical computer or telephone display that's made with conventional LCD technologies. But the yellow one here shows the typical quantum dot display that you would find in today's, for example, if you buy a Samsung television, it will have in it quantum dots. If you buy a new one from last year or this year, it will have inside of it quantum dots, which will have this color gamut that you see here. And the next generation that's now being produced but isn't yet quite available for commercial use follows this white line here that produces an even higher quality set of colors. So this is something which over time you're likely to experience as a display that in which you will be able to have the higher quality colors. Now, there are other technologies that may come in that are important, for example, OLEDs and others, but the color purity of the quantum dot display is actually quite impressive. And if you do come and visit me in Berkeley, you can come and see a whole bunch of these around my lab. Now, the shifting now a little bit, that's the past. We'll talk a little bit more about sort of present and future. So all of what you saw is based off of making particles that kind of look like these, that are pretty uniform in size and which have a discrete number of atomic units in their size across, and that's controlled fairly precisely to make the different colors. Now, in the interim, in the years since this was developed, we have learned how to make these other shapes of nanocrystals. And when I talk about this, I often like to refer to a very famous phrase of Rutherford, who said that there are only two branches of science, physics and stamp collecting. And stamp collecting, I believe, was not considered to be a higher form of learning. And in fact, my students and I, we are very proud stamp collectors. This is our stamp collection, okay? And what I mean by that is to say that there was a period of time when we learned how to take crystals and grow them in the lab in such a way that we could make them have a very wide range of shapes. And what I mean by that is we could make them in rod shapes, for example, but we could go way past that. We could make them branch at will. Not just single branches, but if you like, we could make secondary, tertiary branches and so on. We could make them into this kind of dotted pattern, or we could make hollow crystals where there's a hole inside every one in the middle. Or we could make crystals where there's one crystal, like a Russian doll, completely enclosed inside another. Or we could make ones that look like p orbitals or f orbitals. I mean, we could make lots of different shapes, and they were all made empirically by adjusting the kinetics of nanocrystal growth and other features of the reaction as a function of the time. We could change temperature, we could change concentration of the reaction species, and in playing those kinds of tricks, we learned over a period of time to iterate, to follow empirically what would create this vast diversity of shapes. And they turn out to be really interesting shapes. For example, this is one where there's a little quantum dot right in the center of, it looks a lot like a carbon atom model set. And in the center, there's a small quantum dot. And if you bend the arms, the luminescence changes color. Okay? So it becomes a force sensor that can be used, for example, to measure when one cell presses against another. It bends the arms. By cell, I mean, for example, a tumor cell, as it pushes its way out to become metastatic, will generate a force, and that force, if you get that particle lodged in between, can be measured by how the fluorescence shifts. So these shapes are very important. This can act as a little catalytic nanoreactor where reactants can be concentrated inside and various effects can be observed in that way. So each one of these shapes turns out to be quite useful. But from our position, we're saying that we should follow the admonition of Rutherford and try at some point to actually understand how it is that these things grew. In other words, to try to create a physics out of our stamp collection. And so we're going to do that in a moment. And I'm going to skip over my luminescent concentrator, I believe, excuse me, but I don't want to go over my time, which I think I'm likely to do if I cover too many topics. So I'm going to switch now and go straight to this topic of nanocrystal structure. And I mentioned to you earlier one of our frustrations, which is that I can pretty much tell you where the atoms are inside this crystal, but actually you can see that as it gets close to the edge, it loses our ability to say much about it. And this is a projection, of course, through a dense number of atoms, approximately equal in all dimensions. So we're going through a volume, a depth here that's equal to about this. So you can imagine that when we think about the edge, our ability to say where those atoms are becomes very poor. So we have been trying over an extended period of time to actually find a way to observe the growth of nanocrystals in real time and to observe also all the details of their atomic structure. And a breakthrough for us took place a few years ago now when we learned how to start to grow crystals inside the electron microscope, but in a liquid. And there are some people earlier in their career here. I'll relate a little bit of a story there that I think all the professors can relate to also. So I wanted to do this for about 10 years. And every time a new student would come to talk with me, I would say, you know, let's go and try to make a liquid cell and observe particles growing. And the students would get very excited. And then, you know, you have to talk several times typically before you find a resonance, right? So they would go away, and then, you know, the students would come back, and they would say, you know, Professor, I have this great other thing that I want to work on. And always they would come back, and they would never want to work on that project. And I'm a little dense. It took me like 4 years to figure this out. But eventually I realized, oh, my other students in the group, you know, this person would always go and talk to the students, of course, right, and the postdocs in the group, and they would say, run away. This is one of Paul's crazy projects, don't go near it. Until one day there was a person named Jaime Zheng, and she neglected to go and ask everybody else. And so she just tried, and it turns out that it works just fine. Although actually in retrospect it probably shouldn't have, and yet it does. So it's one of those stories. But in any case, we grow particles inside a liquid cell, and over time we've developed that into a special kind of liquid cell where the liquid is trapped between two layers of graphene, so that the window is a single layer of carbon. And the consequence of that is that the electron beam is not scattered too much by the window. Of course, it is scattered a lot by the liquid, which reduces our background, or creates a lot of background noise and makes it noisy. But you can see here an example in this movie of some platinum nanocrystals. We're taking very heavy atoms now in order to observe them easily. So if you've watched this movie, as it's been running here, what you will see, it has to go back to the beginning and you'll see it again, but what you'll see is small crystals growing inside the liquid. I'll just give it a moment here to kind of start over again. And you'll just see at the very beginning there's nothing there, and then, you know, the tiny crystals start to form. Come on, restart for me. Or you can just see here the results of the final crystals. You can see that they have some lattice orientations, but also some defects inside them because they've been grown too fast, and can't completely control that in the early. There it is, starting at the beginning. So you can see here, you can't see too much, and then all of a sudden you'll start to see small crystals moving around, and they're moving a little bit faster at the beginning, and then they'll start to slow down, and it turns out if you track those motions, their speed is going like 1 over the size, which is what you expect for a kind of diffusive process. And you can see that periodically these crystals will fuse with each other, and those are the characteristics that happen inside that particular system. So here we can observe the growth of this crystal. Now, there's lots of details inside that I'm not going to go through that we've studied over several years, but what I want to go do is to this problem of the surface so that I can illustrate to you the aspects of the future in a sense. So imagine that we take in that movie one of those crystals and we simply observe it as it's moving, and now we subtract the center of mass motion, so we make it so that in each frame the crystal is in physically the same location, but of course it's rotating. So inside the liquid, the crystal is spontaneously showing all of its orientations, and as a consequence we can observe this series of diffraction patterns from that single particle. And so this would be an example, for instance, of a particular example of a single particle, and these would be diffraction patterns where the background has been subtracted, and what you'll see is that we observe many different orientations. And in the limit where we've collected, say, 1,000 or so of those kinds of diffraction patterns, we actually now have enough information to go back and obtain the electron density of every position inside the crystal. And so that's done by a kind of simulation, in which we start with a uniform density and we see what kind of diffraction pattern that would create. And then we fluctuate, we allow a fluctuation, a Monte Carlo-like variation in the electron density, and we see if that gets closer or not to the observed distribution of diffraction patterns. And then we repeat that over and over and over again with both a discrete and a continuous region to that process. And if we do that enough times, eventually we're able to back out the best fit that we can get for the amount of data we have and the amount of noise that's there. And what we can get is the position of every atom in the crystal to a resolution of just a little bit worse than 2 angstroms, 2.14 angstroms. Now, the reason this is important is because the nanocrystals that we know how to make, no two of them are absolutely identical the way proteins are. They just are not, because we're not as good as nature is at making stuff with 1,000 atoms yet. But we are going to learn, and we'll get better at it as time goes on. And the way to get better at it is to observe single particles. So this is an example. To my knowledge, this is actually the first example where the position of every atom inside a sample where every crystal is not the same, which is a typical human-made construct of this size, we can observe the electron density inside it. You saw earlier that these particular crystals like to fuse, and so these are some of the fusion events that have taken place. And if we look, for example, there's a grain boundary where some crystals fused, and we can go in now and say, here are all the atoms, and you can see this grain boundary is not flat. And in fact, what happened in this particular crystal is that a 110 and a 100 face collided at a asperity at a single point, and then atoms filled in around from the sides. We could see that in the movies, and then they made a flattish surface, but in fact the grain boundary, if you move all the way through the crystal, actually has roughness and fluctuates inside of it. It's not a completely flat grain boundary the way you might think it would be if you could only look at a single projection. Now, this is not quite yet good enough to obtain the positions of the atoms here at the surface, but it's close. And our goal is going to be to do some experiments in the near future where we are able actually to observe a core shell interface. I showed you earlier core shells. We're in the process now of measuring in some detail some core shell interfaces where we think we'll be able to see in some detail the surface reconstruction. So it will be a first version of getting at where the positions of the atoms are inside one of these tiny crystals. How am I time-wise? Do I have a few minutes, or I'm okay? Okay. So I showed you an example where we've obtained the structure of a nanoparticle, and it wasn't a perfectly formed particle. I told you at the beginning that you could form particles that are quite perfect, but I think I reminded you, if you grow them too fast, even a tiny crystal can be messed up, and ours had these grain boundaries inside them, which we did as an exercise. Partly we wanted to see that so that we could find some richness to a structure that we could observe by this technique, and then slowly refine it from there. But another thing that we can do, we cannot yet make all those shapes, the stamp collection that I showed you, we cannot yet make those in the electron microscope. We've been trying, but we can't vary the temperature and the concentration as a function of the time as intricately inside the electron microscope as we can in a flask that's controlled outside. So we can't quite make all of those shapes, but what we can do is take shapes that have been made in advance and make them go away by etching them. So here is an example where we have an etchant, in this case an iron 3+, that will etch a gold nanoparticle. And you can see that if we expose it to etchant, then the gold nanoparticle is slowly dissolved. So here you see some movies, and in fact Chad has done beautiful work with making many different shapes of noble metal nanoparticles, as have several other really wonderful people in the community. So nothing that we've invented here, but we've taken all these shapes which have been reported in the literature, and we've grown them, and then we place them inside the liquid cell, and we destroy them. So rather than growing the crystals, we're taking them apart. But as you know, those two are cousins. So if we study how we can take them apart, we'll learn a lot about how they form as well. And so here you can see all of these etching experiments, and you can see that different shapes are etched and controlled in different ways. You'll see, for example, in a few movies that they etch a little ways, and then they seem to get very stable for a little while. Little tiny particles will form because atoms have been removed and you supersaturate the solution, so new crystals can form inside there. But you can also see that these shapes evolve in very, very complicated ways. Now, it turns out that we can convert this into real science. And the first thing that we can do is simply take these rods and make many of them and track how their dimensions change. So we can make a plot, and if we do that, what we find is that under all other conditions being fixed, the rate at which the crystals disappear is simply related to the curvature. The more the crystal's curved, the faster it's etched. And that's easy to understand because a curved crystal has a curved facet has essentially broken or weaker bonds at it, so it becomes a spot that can be picked off more easily by the etchant. And so that's quite a simple idea. So we can make this kind of contour plot that shows, again, how a crystal disappears. Sequentially, these are each units of time, and what you can see, of course, is that it appears as though atoms are being lost from the curved end a lot faster than they're being lost from the flat side. So we can take this type of diagram and simply color code it. So we make what we would call a time domain contour plot. And in this contour plot, what we do is we say the color is proportional to the curvature. So the hotter colors are the higher curvatures, and then the contours represent the evolution of the shape as a function of the time for crystals that are not rotating. Done. Okay. So I'm not going to go through all the details then, because I'm told that I'm done. But what I'll say is that we can make these diagrams that look, for example, like this, where you see these time domain contour plots. And if you go in and you look at them in some detail, it turns out that we can actually explain in some molecular detail why all the shapes that people have seen in the literature are showing up in a very quantitative way that differentiates between slow and fast growth and other features like that. So the liquid cell is now moving into a stage, I think, where it's becoming extremely quantitative, and it's going to become a very powerful tool. I'm going to wrap it up there and just thank you and say that, you know, it's been a real pleasure to be here with you and to share with you a little bit of our story of how we've been developing this building block of nanoscience, the nanocrystal. And it's been fun to see them find their use in the real world, and also now to make a cycle back into the fundamental science of these materials and to try to understand how it is that they form, how they disappear, and how we could eventually know a lot more about them. Thank you for your attention.
Thank you, Paul, for a very stimulating talk. We can allow one question from the audience, please.
A layman's question. Have you tried to develop autopoietic structures within tissue and control function by modifying structure and captivating this by
No. We have not, so what we have developed a lot of these probes which can be biofunctionalized and introduced inside different environments. So people have done, colleagues and other research groups have certainly grown tissue, proto-looking tissues like acini and things like that with quantum dots present. and have observed evolutions of behaviors. But to say whether, I mean, typically the approach people have taken has been to think that the quantum dots are simply spectators and not influencers of the, shapes that are being formed. As to whether that's truly the case or not, which seems to be the implication of your question, I actually don't know, whether that's, so it's an interesting question and I hadn't really thought about it, but it might be possible, yeah.